Okay. Yeah, so good morning. Welcome back. So let me start by just giving a quick recap of what we did in the first lecture. So we started off with kind of this fundamental fact that the universe is expanding. And because the universe is homogeneous and isotropic, so it's the same in every direction and the same at every point throughout the universe, it can be described by the simple relationship the distances are expanding by the scale factor. So there's a single function in time that describes the evolution of the universe. And then we even derived the fundamental equation, the Friedmann equation, that describes this evolution of the scale factor in terms of the total energy density of the universe averaged over all of space. Okay? Now, to close the system of equation, we then had to stipulate how each of these densities scale with the scale factor, how they dilute when the universe is expanding. So the matter density just dilutes by the volume, the radiation density dilutes by volume, and the energy decreases by a redshifting effect. And then, somewhat surprisingly, this dark energy density actually doesn't dilute at all. So the energy of any region of space kind of increases as the space gets bigger, which is, of course, rather strange. Now, when you take these scalings in the energy density, you get kind of specific power law behavior in the evolution of the density with the scale factor. So here I've plotted this again on a log-log plot. So these become straight lines with different slopes. And so radiation density increases the fastest as we're going back in time. So at some moment in the history, the universe was dominated just by radiation. And so that's what we call the hot Big Bang. The universe is hot and dense and populated by relativistic particles. But then, as you can see, as the universe expanded, it cooled, and there was a transition where radiation goes to matter and matter goes to dark energy. And so the universe goes through these three different phases in its evolution. Okay. So then finally, in the last part yesterday, I discussed what this means for the hot Big Bang picture of the universe, so that there's actually many interesting things that happen on a short amount of time. We started with the matter-antimatter asymmetry, which is not an established fact how that happened, but we believe there must be some mechanism that created an asymmetry between matter and antimatter, roughly at 10 to the minus 19 seconds after the Big Bang. The most certain event that we maybe have is this 10 microseconds after the Big Bang, which is the QCD phase transition, where the individual quarks and gluons combine into protons, neutrons, so the hadrons, but also pions and other hadronic particles. Okay. Then something very interesting, at least to me, is 1 second after the Big Bang, the weak interactions became ineffective, so the neutrinos weren't kept in thermal equilibrium with the plasma, so the neutrinos started to free streaming, and in fact these neutrinos are still around us as the cosmic neutrino background. Okay? At early times, they still have a significant contribution to the stress tensor, to the energy density of the universe, so 40% of all of the radiation in the early universe were neutrinos. At later times, actually much later, after the formation of structure, neutrinos became non-relativistic because, as you know, they have some little mass. And in fact, we can use cosmological observations to try and put bounds on this mass and maybe even detect neutrino masses, the absolute value of the neutrino masses, which we don't know from cosmology. Okay? But these neutrinos are extremely low energy neutrinos. We can't measure them even if we have enormous water tanks of trying to kind of test these collisions of neutrinos with ordinary matter. But we can see their indirect effects on the cosmic microwave background. Okay? And actually even an indirect effect on the clustering of galaxies that I can describe if you're interested. So then the next interesting event was 3 minutes after the Big Bang. That's when the first light elements were forming, mostly hydrogen, helium, and lithium. After that, the universe was expanding too rapidly for the particles to meet and form stable nuclei. The remaining stable nuclei were formed inside of stars or in stellar explosions. And then the last two things I mentioned was the formation of the first atoms. So when the temperature dropped to roughly, I think, 0.1 eV, okay? Let's see. You can check my book, whether that's correct or not. It's less than, so normally, maybe it's 1 eV, not 0.1. It's a factor of 10 smaller than the ionization energy of hydrogen. So the ionization energy of hydrogen is 13.6 eV. And so when the temperature has to drop actually to 1 order of magnitude smaller than the ionization energy of hydrogen. Any ideas why that's the case? Why isn't it enough for the temperature to drop below hydrogen? The basic idea is that once you drop below hydrogen, you might think that there's not enough energy to ionize atoms, and so atoms become stable. Why does it take a little bit longer? You have to drop in temperature actually by a factor of 10 more. Any guesses? Yeah?
Is it because the Planck spectrum has a really long high-energy tail?
Exactly. It's because there are many more photons than matter particles by a factor of 10 to the 10. And so you can go a far distance into the Planck tail of the spectrum where the energies are actually higher than the mean energy of, and those very high energy, they're exponentially few of those, but we also have an exponentially large number of photons relative to the number of matter particles. And so you can go far into the tail and use those high energy photons to ionize. And so you need to shift the mean value of the photon energy to a factor of 10 smaller, such that even the largest energy photons don't have enough energy to ionize things. Okay? Okay, and then finally, so this is a very important event because the photons then for the first time were free streaming. We can still see this, just like the neutrinos are streaming through us right now. These photons are also streaming through us right now. We can measure them now relatively easily, and we will see that they have interesting fluctuations across the sky that we can analyze. In fact, these fluctuations that we can see in this first light, they're indicative of fluctuations in the matter density in the early universe. So there's small fluctuations in the density. Over time, those small fluctuations in the density will grow. They will, matter will cluster and form galaxies and stars and planets and so forth. That takes a long time, billions of years, but it's the mechanism by which all of the structures that we see around us has formed. Okay? So I want to highlight that this timeline that I've drawn here is just a fact. There's no way you can say this is just a theory and so on. This is just a fact as much as evolution is a fact and the history of the Earth is a fact and things like that. So this is just an observational fact. There's no speculation, very little dependence on theory and so on. Okay? And in fact, we will see this, especially the observations of the cosmic microwave background, probe very precise details of this picture. So there's very little wiggle room to, there's not much room to add anything more into this picture than what I've described. Anything you want to add, you have to add at high energies where we're less certain about what the physical processes were. Okay? Okay, are there any questions about this? Yes?
Yesterday it was mentioned that it was very difficult to calculate the distances of certain objects.
Yes.
But why is it like that if it seems like just a problem of calculating the expansion and maybe its closest, strongest gravitational interaction? And
sorry, say it again, the last part?
It seems like just a problem of calculating its expansion, well, taking into consideration the expansion.
Yes.
And its strongest interaction with the gravitational object.
Yes.
And
so it's actually, let me clarify this. So it's not a problem of calculation, it's a problem of measurement. How do you measure the distance to something that if you can't, how I would measure the distance to the end of the room, I would take a ruler maybe and lay it, back to back to back and walk up there. Okay? So we can't do this for stars. So all the measurements of distances are indirect, using the light that we receive from the stars. So for the closest stars inside of our galaxy, the way we do this is we look at a star, we wait for the Earth to travel around the sun, and then we keep looking at the star, and the star will shift in position because we're looking at it from different angles. In particular, half a year later, we're looking at it from the opposite side of the orbit, and there will be a shift in the position, and that, by geometry, that shift in the position is larger when the star is closer to us. So we can use this so-called parallax of the stellar positions to measure distances. But that only works for very nearby objects, because if you go further away, these angular shifts become smaller and smaller, and at some point they become smaller than the resolution of our measurement. Okay, so for the smallest things, we can use that. If you go a little bit further, the next trick we use is we use these so-called Cepheid variable stars. So there's a special type of star that was discovered by Henrietta Leavitt, I think, way back, that actually pulsates in its intensity. There's a pulsation. And she discovered that the period of that pulsation is correlated with the absolute luminosity of the star. And so absolute luminosity means you actually know how much power, how much radiation it emits locally at its location. And then you can compare that absolute luminosity to how bright it appears on the sky. Because something that's bright on the sky could either be bright because it's very nearby and we see a lot of the radiation, or it's intrinsically very bright but it's actually far away. You don't know. And so you need something else to correlate with to decide whether something is bright because it's nearby or something is bright because it's intrinsically bright. And so you use these Cepheid-varied pulsating stars to do that. That also works to up to a certain distance, and then that stops. We can't measure these Cepheids arbitrarily large distances, and that's when you use special type of supernova explosions that we also think of as standard candles and so forth. So it's difficult. There's actually not just one trick pony that works. You have to use different types of distant measurements for different distances and objects and so on. Okay? But it's not a problem of calculating. GR is a perfect theory of the geometry of space-time. We can calculate perfectly. If we know the absolute luminosity, we can calculate everything perfectly. No problem. Okay. Yeah.
What are your thoughts on JWST's relatively recent observations of galaxies forming like 330 or 300 million years after the Big Bang instead of 1 billion years?
Yeah, it's interesting, but I don't think it's a crisis as it made out to be maybe on Twitter or so. Sometimes this is then promoted as like the Big Bang is wrong, everything is wrong, and people love things to being everything wrong, and Einstein was wrong, and so the much more mundane kind of resolution to all of this is that we still have to tweak our numerical simulations of galaxy formations, and if there's a lot of uncertainties in how galaxies will form. In fact, we will discuss a little bit of that today, and it's much more likely to me that those uncertainties in the simulations, if you actually look at the simulations, they have a lot of free knobs that you're turning that are not built based on fundamental physics. They're based on kind of phenomena, just like fitting the data, roughly. And so I think, my very, very strong suspicion is that these things will resolve it themselves when we understand these simulations better, rather than the Big Bang being wrong. Precisely for the reason that the Big Bang works so well in everything else. Yeah? So you're giving up a lot by saying, just because of this one observation of something that I don't have good simulations for, I'm willing to throw out the formation of the light nuclei, the CMB, the formation of structure, the entire picture of the hot Big Bang is just like so self-consistent and you have nothing to replace it by if you say the Big Bang didn't happen this way. So it's Okay, let me move on maybe because we have some stuff to cover today. Okay, so what I want to discuss now, so what we discussed last time was just the homogeneous evolution of the universe. We didn't consider fluctuations, we just averaged over the entire observable universe, and we asked how on average the universe evolves over time. But now the next important feature, of course, is to explain why we are here, okay? And why kind of there's structure around us, why there's a galaxy, why there's stars, why there's planets, and so on. So for that, we need to go beyond this simple description of the universe in terms of just an average density. There need to be fluctuations, okay? In fact, so here on the right, I'm showing you a picture of, galaxies, strewn across the sky, so light from these galaxies. On the left, in fact, I'm showing you also light on the Earth. And so it's actually also in cosmology, it's a tricky business of kind of gauging from the distribution of light, where all the mass in the universe is, just like for the Earth, Just measuring the light, at night is not a faithful representation always of where kind of all the land masses are, because certain areas are more populated than others, okay? So also in cosmology, you have to be a little bit careful, but actually in cosmology, I think it's easier. So very roughly, it's still the case that light traces the dark matter, and you can measure the dark matter indirectly by gravitational lensing, for example, and test this relative clustering of light and dark matter and so on, okay? And so one interesting feature that you find when you analyze these fluctuations, and you can see it by eye here, is that things are not distributed randomly across the sky. So it's not the case that some supernatural being decided, like we throw in a galaxy, with a random number generator across the sky. But there's something very structured that happened, some physical mechanism that actually created correlations amongst these different density fluctuations or galaxies in the sky. So these things are not distributed at random, but they have interesting correlations, and one of the main goals in cosmology is to explain these correlations. Why aren't they distributed randomly, but what creates some very specific physical correlations between the objects. Okay. And so just to give you the answer, that we very strongly believe that the reason there are these correlations is because of a fascinating connection between the physics of the very small and the very large. So these correlations really span millions of light years, but we think they were generated by physics operating on microscopic scales, even smaller than the scales that are being probed here at the LHC. Okay? So what we actually think happened is that there were random quantum mechanical fluctuations in the vacuum. So you already heard probably in other courses that the fields are fluctuating randomly because of quantum mechanics. The universe at that same time went through a phase of very rapid expansion that we call inflation that turned actually these quantum fluctuations into classical fluctuations when these wavelengths of the fluctuations got stretched enormously. And it's those classical density fluctuations that then provide the seeds for everything that follows afterwards. Okay? So what happens at first is that these fluctuations in the density will excite sound waves in the primordial plasma, just like pressure waves in air are being excited here in this room. It's, in fact, we have seen, and I will show you later precisely, that we have seen the imprint of these sound waves in the first light in this cosmic microwave background. So you see fluctuations here in this picture of the intensity of the light in red and blue spots. That corresponds to, dense and underdense regions, so more and less matter across space. And then over time, these things, as I said, will cluster. It's a process of where the rich get richer, where more, if there's matter in a certain region of space, it will attract matter from the surrounding space and empty the space around it, and things get more and more clustered by gravity. And so that's the mechanism by which then galaxies and stars and everything else forms. So that's the basic story. I'm going to tell the story backwards, okay? Meaning I'm first going to describe this gravitational clustering of small matter fluctuations at the time of recombination until the moment when galaxies form. Then I will describe the impact of these sound waves on the cosmic microwave background. And then in the second lecture today, I will talk about these quantum fluctuations providing the seeds for everything else. Okay? So that's the timeline of the rest of these lectures. And so finally, of course, just to highlight, because this is a connection between microscopic and macroscopic physics, we can use it as a probe. So we can use observations that we make over cosmological distance scales to learn something about physics on microscopic distance scales or extremely high energy scales if you want. Okay, so let me describe a little bit in more detail how this gravitational clustering of density fluctuations works. I'm just going to describe it a little bit schematically in pictures. There's an appendix to these lectures again, where you can actually derive the relevant equation in very much the same way we derive the Friedmann equation. Okay, and let me actually just describe in words why that's the case. So the picture is the following. Imagine that there's a spherical overdensity in a homogeneous universe. So there's a universe that has an average density rho bar of T, okay? And then we're carving out an extra sphere, and that sphere has either an over or under density, has a different density rho. That's not quite the average density. And so we're interested in the evolution of the so-called density contrast. So as long as this density rho is not enormously bigger than rho bar, we can define this fractional density little delta, which is the fractional difference between the density in the spherical region and the average density of the universe. Yeah? So you take that density, subtract off the average value, and divide by the average value to get something dimensionless. Okay? And so it's this delta that we would like to describe. And we can describe it perturbatively as long as this delta is smaller than 1. And as soon as delta reaches values that are close to 1, that's a critical value where actually this overdensity will decouple from the expansion of the universe and collapse into a stable, virialized galaxy cluster or galaxy. Okay? So there's a critical value in this delta. We're not quite going to describe this critical value. You can even do that for a spherically symmetric distribution, even this non-perturbative evolution of the density contrast you can describe, something called the spherical collapse model. We're not going to quite do that. We're just going to do the approach to this collapse as delta remains small, and we can expand the perturbations order by order in small delta. Okay? The equations, I mean. All right? So in fact, these equations are analyzed in this appendix. Okay, so if you really care, you can go after the lecture, go to the end. There's kind of 3 or 4 pages where I actually do this derivation and show you how little delta evolves in time in the different phases of the history of the universe. Okay, but here I'll just quote the results. I will just tell you what the answers are, but you can see the precise derivation in this appendix. So first of all, if you assume, of course incorrectly, if the universe is static, it's not expanding, so that this background density rho bar is not a function of time, but it's just a constant, then actually what you will find from the equations of this evolving overdensity, you will find that it grows exponentially. There's an exponential instability in a static universe for this overdensity to collapse. Okay? So this happens exponentially fast. This exponential instability in an expanding universe turns into a power law instability. It's just because the expansion of the universe kind of counteracts a little bit the tendency of matter to collapse. So in Newtonian gravity, if in flat space without any expanding universe, this collapse happens very efficiently. But if the universe is expanding, of course, it has a tendency of pushing things apart, and so this collapse, naturally, you expect not to be as efficient, and it changes from exponential to power law. So in fact, in this appendix, you will derive that during the matter era, this delta evolves as t to the 2/3, okay? And since you all followed me perfectly last time, you know that t to the 2/3 is exactly how the scale factor evolves in a matter-dominated universe. So this density contrast actually evolves with 1 power of the scale factor during the matter era, okay? During the radiation era, however, it only evolves as a log of time. And as you know, log is a very flat function when you go to large times. So it's a very inefficient growth. It's almost constant. It's almost not growing. It's almost like just frozen, okay? So during radiation-dominated era, this overdensity will not collapse very efficiently, just logarithmically. Often we just ignore this log and say it's just constant, frozen, okay? So this means you actually have to wait. In order for this clustering to happen, you have to wait until the universe becomes dominated by matter, okay? And in fact, it's actually very important that the universe is dominated by dark matter. If dark matter wasn't there, and it was just the baryons, then matter-radiation equality would happen later, okay? And you would actually not have enough time for the clustering to be efficient enough in order for galaxies to have formed in the right amount of time for us to see them now, okay? I don't know if Bradley discussed this in his lectures on dark matter. But it's one of the really nice and intuitive and pencil and paper arguments for dark matter, that without dark matter, this growth of the density fluctuations is not efficient enough. You need this head start coming from the clustering of dark matter to then have the baryons fall into the potential wells that the dark matter creates and things to cluster fast enough. There's a timescale problem. If you take the dark matter away, galaxies will not form fast enough. Okay? All right. Any questions about this? All right. So now one slight complication here, of course, is that real density perturbations in the universe are hardly spherically symmetric. So this was highly idealized. Actually, roughly speaking, maybe one thing that maybe I should have mentioned in this, when we do this derivation of the spherical overdensity, you can think of the spherical overdensity really as a separate universe that has positive spatial curvature. Remember yesterday we discussed kind of the 3 different cases where the universe is spatially flat, positively curved and negatively curved. If something has larger than the critical average density, it will act like it was a separate closed universe, and it will evolve according to the laws of basically there's a local Friedmann equation that describes this, and it's this local Friedmann equation that we turn into an evolution of this density contrast. So that's roughly how the calculation goes. That it's not actually really a new calculation, it's just like separating out an overdensity and studying its evolution according to the locally homogeneous case of that averaged spherical overdensity. Okay? Now, of course, this was idealized. The real fluctuations in the universe are not spherically symmetric, so what do we do? Okay? They have some more complicated, random pattern of density fluctuations. So the standard trick, of course, that we use in physics is to decompose this, and so here I've shown it in 1 dimension, decompose the complicated pattern of fluctuations into its individual Fourier modes. Yeah? So different sine wave components with different amplitudes and phases, as I've shown here. And then we have the density contrast delta of x is represented by an infinite number of density contrast delta of k, where k is the wave number, inverse of the wavelength, okay? And it turns out that each of these delta of k does satisfy the equations of a spherically symmetric mass distribution, just because the universe is statistically homogeneous and isotropic, and that gets reflected in the Fourier components. So we can then import, in fact, these equations that I've not shown you, but you can see if you're curious in the appendix. Those equations actually precisely are the equations that the individual Fourier modes satisfy, and so you can calculate individually how each delta of k clusters, And in particular, its time dependence will be exactly the one that I showed you with log of t and with t to the 2/3. That still holds. But its spatial dependence will then come from the initial conditions, whatever the initial values for these Fourier modes were. Okay? That's just maybe a technical aside, how we can turn this idealized calculations of the spherically symmetric overdensity into a kind of the real calculation when we use Fourier modes. Yes?
So what will be the fundamental frequency here?
Sorry?
What will be the fundamental wavelength of these Fourier modes?
There's no fundamental, well, we will see actually that when we come to describe these Fourier modes for the primordial plasma, there's something extremely interesting that I don't want to take my punch away now, but I will show you. Maybe I do, okay. Science is not a mystery story, so maybe I can tell you now. But actually, so what happens is that the universe has a finite size given by the light travel time. So there's a physical horizon to the universe that depends on the age of the universe. So because of the hot Big Bang, the universe started at a fixed moment in time, and then at a finite moment sometime later, in particular, for example, at the time when the first atoms formed, the universe was 370,000 years old, and light traveled a finite distance at that amount of time. That provides actually a finite cavity to the universe, so to speak, that causal influences can only operate on that length scale. And so then these sound waves that I mentioned will actually propagate as standing waves within that cavity. That you can get interference like standing waves in a pipe or in some kind of closed, the air waves kind of have fundamental frequencies that are related to the size of the cavity. The size of the universe provides kind of the fundamental frequency of these sound waves in the universe, and there will be higher harmonics. And we saw these in the sky. It's absolutely freaking amazing. Yeah, that I will show you. The picture of the correlations that we see in the first light are coming from these standing waves in the cavity set up by the universe. Okay, we will get there in not so long. All right. Other questions? It's one of the greatest things you ever see in science. I can promise you. Okay. Okay, but before we get there, so I've now turned kind of this problem into the problem of spherically symmetric matter in the spatial distribution into this kind of statistically isotropic distribution of Fourier modes. It turns out when you take the square of the amplitudes of these Fourier modes, it defines the so-called power spectrum of the map. So if you have some map in real space with high density, low density, not randomly but kind of correlated, the way you often analyze this, take the map, you Fourier transform the map into its individual Fourier components, and the square of those Fourier components is the so-called power spectrum. Yeah? And then if you go back to real space, by Fourier transforming the power spectrum, we get the so-called two-point correlation function. It tells you the relative probability of dense regions as a function of their separation. So if I'm observing, for example, a galaxy, a dense spot here, what's the likelihood of observing another galaxy at some certain radius? That's what the two-point correlation function is telling you. And the power spectrum tells you precisely that function of distance across the sky. Okay? Of course, it's a statistical quantity, so what I really mean here is that you take any 2 points with a fixed separation, and then you move that kind of, those 2 points across the entire sky and average over all possible. So you have some density here, you multiply them, get some number, you move these 2 points across every point in the sky, always multiply the density numbers that you get, and average over all these measurements, and that tells you the two-point correlation function. Okay. And so this is a measurement of the two-point correlation function of the matter power spectrum. Okay. The different traces basically it's the dark matter distribution. The different traces of doing that, on the larger scales, you actually use the cosmic microwave background to tell you how the dark matter is clustered. On shorter distances, you use galaxy clusterings, and on the very shortest distances, you use something called Lyman alpha fluctuations. Okay. And so as you can see, it actually has a relatively simple shape. Okay. So there's a peak, there's a power law scaling that you can check goes as 1 power of k here, and then it goes as 3 powers of k minus 3 powers of k here. Sorry, I'm never going to learn how to operate this pointer. Okay, and then there's a peak. There's a characteristic scale that's imprinted in this power spectrum. That scale is the size of the universe at the time when matter and radiation became equal. Okay, the matter radiation equality. And the reason that scale gets imprinted is because, as I showed you earlier, fluctuations evolve differently depending on whether the universe is dominated by radiation or matter. So the scales on the left of this peak are the largest scales. Those entered the horizon when the universe was dominated by, let's see, radiation. No, matter. Right. Yes. Yeah. We can figure it out on the board later. It's too early for me to do this on my feet. Okay. While those that are the fluctuations that are on the smallest scales, the smallest scale enter the horizon first. So those are radiation. Yeah. Okay. I'll repeat because I figured it out. Now I'm going to repeat it clearly. Okay. So the smallest scales are the ones, because the horizon is growing and actually the fluctuations were outside of the horizon to begin with for a reason that we will discuss in the next lecture. And so then the smallest scales enter the horizon first, and they will evolve according to these evolution equations that, for example, during the radiation era, it will evolve as log t, while during the matter era, it will evolve as t to the 2/3 faster. Okay. And that creates a difference in the, basically the fluctuations actually get suppressed on smaller scales because there was less growth of those fluctuations during the radiation era. Okay? So, this is a bit of a detail. It's just telling you that we understand very well the shape of this curve. And you, in fact, in principle, after you read the appendix, you would know enough to reproduce the shape and even the precise scaling of these curves. Okay? Any questions about this? Yeah. Let him first.
Pretty small question. When you were talking about calculating with the Fourier modes, you mentioned that you sort of approximate like a small part of the universe as like the whole universe for the calculations, if I heard you correctly. Are those like what you define as the galactic clusters?
Okay, so no. So actually, first of all, when I made that statement, I wasn't even talking about Fourier modes yet. I just said, in real space, imagine an overdensity, some region of space that has higher than average. And I haven't even told you exactly how big that density is. In fact, how much larger the density is relative to the background density depends on my choice of size of region. So if I make this sphere, for example, larger and larger, at some point, if I make the sphere infinitely large, it encompasses the entire universe, and then by definition, it has average density. The question is now, if I make it smaller, and then it doesn't, because the matter is not distributed uniformly, depending on where I put the sphere and how large I make it, it will have an overdensity. And it's that overdensity that I'm tracking in time. But it could be, for example, this sphere could be so large, and typically it is, in these calculations, taken to be so large, that encompasses many galaxies. Yeah? In fact, galaxies haven't even formed yet. So because we start with small delta, delta will grow, and once delta becomes of order 1, things become complicated. Then this thing will split in pieces, will form individual galaxies, and you form a cluster of many, many galaxies that originated from this kind of spherical overdensity. So we're describing some kind of average trend first on large enough scales, and then later on it becomes non-perturbative, and you need to use numerical simulations to see how this thing fragments into kind of the objects that we observe. Yeah.
So regarding when we were considering the spherical overdensity, it was said that we are considering a positive space curvature, but it wasn't clear to me like if it was like on the radiation era and then you change. Nowadays we tend to opt for a flat curvature. Well, a flat universe instead of a positive or negative curvature. Yes. So that means that if we change to our matter era, the curvature changed, or?
Sorry. So there was an average density of the universe that's still described by a flat universe. When averaged over the entire observable universe, it's still the case that we observe it to be approximately flat. All I'm saying is that locally, on much smaller scales than that, much less than so this average density is reached when you go larger than 100 megaparsecs. Let's now imagine we take this sphere to be smaller than 10 megaparsecs. Then there can be statistically random fluctuations amongst, around the average, just because there's structure that wants to form. And it's those things that can be, if it's a void, it would be an open universe that expands faster than the average. If it's an overdensity, it's a closed universe that wants to collapse. And those collapsed regions are the ones that eventually then form galaxies. Okay?
Okay, thanks.
But, I need to move on, just because there's actually more things to, yeah. Okay, so So okay, this was remember that I'm going backwards in time. So I'm first describing to you how small density fluctuations cluster into large density fluctuations, galaxies and stars and planets. That's the part that we know the kind of sketched. And now I want to go back and describe how these small fluctuations that you see in this picture here, how they formed from kind of some earlier initial or primordial density fluctuations. So this is an amazing picture. That's kind of the picture taken by the Planck satellite that shows us the intensity of light as a function of direction on the sky. So this is a map of the entire sky. We have these hot and cold spots. I mentioned last time that the average temperature of this radiation is 2.7 degrees Kelvin, so extremely low temperature radiation. But on top of this 2.7 degree Kelvin, there are these fluctuations of the order of magnitude of 1 part in 10,000. So there's kind of 100 microkelvin variations of this temperature from hot to cold. Okay, and this looks now very random to your eye, maybe, but it isn't random if you take the Fourier transform of this map, extract the Fourier components, square them. That's the power spectrum, and that power spectrum or two-point correlation function has structure in it that we will see. Okay, in fact, this is a picture of that structure. It's clearly not random. Okay. And it clearly has some peaks and troughs, so it's already giving indication of this kind of oscillating waves that I was mentioning in my answer earlier. This is really an imprint. The fact that there are these high peaks in the power and lower troughs in the power is a reflection of standing waves with different wavelengths interfering constructively or destructively in the cavity set by the size of the universe. Okay, so actually, to understand what the power spectrum really means, I've stolen this figure from a friend of mine. So imagine we have this is what the picture looks like. But now instead of looking at the complete map, let's actually filter it, meaning that you kind of you're picking out certain wavelengths or you're choosing a certain resolution for your picture. So this is what I've done here. I've selected out just the largest length scales. So this is this band that I'm showing you here on the left. If you take the power spectrum and you filter out everything except for this band, this is what the map will start to look like. Okay, I filtered out all the small scale fluctuations, so you don't see anymore on small scales hot and cold spots. You only see very much larger blobs. Okay, because the very largest scale actually corresponds to 90-degree angles. That's the largest we can measure, and then this corresponds to like 10 degree roughly on the sky. You could measure from these spots here. Okay, so we have only looked at kind of the largest 10-degree fluctuations. But now what I'm going to do is I'm going to step through this power spectrum. I'm going to choose the band to move towards the right. Yeah. So we're going to have then we're going to start including shorter and shorter, or looking at shorter and shorter fluctuations. So this is what happens next if I move one band over. Next, okay. So by eye you can probably see that the strength of the signal is roughly constant. So although you start to include smaller and smaller blobs, the intensity of the image doesn't really change. But now you have to carefully focus on the picture once I go through the large peak, because there should be an increase in brightness once I go through this peak here. Do you see it? Actually, maybe we go back and forward. The first one is brighter than the next one, no? Maybe. But that's what it means, that actually that the intensity in this particular band of fluctuations is larger. And then as I go further, you start actually seeing damping. This damping is actually mostly coming from the neutrinos in the early universe. And so there's a damping of the fluctuations. It's also interesting physics, but let me skip it. If somebody wants to know how this works, it's actually very interesting. Yeah. It has to do with the fact that this primordial plasma is not really a fluid. There's a finite mean free path of the photons, and the shortest distance scales are smaller than the mean free path of the photons. So the photons can randomly walk out of hot and cold regions and kind of equilibrate the temperature, and that suppresses the temperature fluctuations on the shortest distance scales. Okay. So we understand extremely well where this picture is coming from, and now I want to actually describe for you where these features actually are coming from in more detail. So first of all, and I've mentioned this in passing already at various stages, that at early times the photons and the baryons, and here baryons are mostly protons and electrons, everything else is kind of subdominant. There's of course a lot of helium as well, but it's smaller by number than the protons. So these photons and baryons initially are very strongly coupled to each other by the electromagnetic force. All right? And so in cartoon form, you can kind of have the baryons and the photons coupled, almost like a mass coupled on a spring. And then there's a driving force that's created by the dark matter fluctuations that kind of, yeah. And indeed, in fact, you could write down a differential equation for the evolution of the fluctuations in this plasma, which is the equation of a harmonic oscillator with a driving force on the right-hand side given by the dark matter and a friction term given by the expansion of the universe. It's a very intuitive equation that if we had time and another appendix, we could also derive, okay? But so in cartoon form, this is what it is. It's a harmonic oscillator with some weight. The weight is provided by the baryons. The restoring force is provided by the pressure of the photons. So if you try to take these, and it's the same as for sound waves in the air. If you try to compress the air, it will bounce back. There's a restoring force. Here in the early universe, the restoring force is given by the pressure of the photons. Okay? And so therefore, the dark matter will kind of provide the ringing of these sound waves, and then the photons will make the sound waves kind of oscillate with constant amplitude. And then the pattern that we see in the CMB is a superposition of many, many of these sound waves. Okay, so this is a picture on the left. There's a picture in real space. Imagine you have kind of localized density fluctuations. And so those localized density fluctuations, let's see actually what happens to a single one of them. Imagine you take one density fluctuations and almost like a delta function, where you just put it at some specific position in space. Because in physics, if you understand the evolution of a delta function, you kind of get the Green's function evolution, and you can convolve it with the total density to get what the system does in full generality. So the response of a system is often characterized by just understanding a single localized perturbation. So that's what I'm doing here in this picture. In principle, this would now be a movie, okay? The movie would be the following. There's this density fluctuation. The density fluctuation has two components. It has the photons and the baryons that are strongly coupled to each other, and it has the dark matter. So there's actually two spikes here with different colors, okay? Then I hit go, and the movie goes, okay? And so what happens initially is that the dark matter will just stay put, because dark matter is pressureless. If you have dark matter at a fixed location, an overdensity that's very localized, it will not spread very far. Okay, it will remain a peak like this. But the photons and the baryons, because they have pressure coming from the photons, will move like a ring-like perturbation outwards with a fixed radius. Okay, so this is what the end of the movie then looks like. It's a pretty boring movie, so you can I think guess what the evolution between those two snapshots. Okay, so in green you're seeing photons and baryons. In the orange you see the dark matter. The dark matter stays at the center, and there's this ring that's also called the sound horizon, the maximal distance that sound can travel. And so that actually creates a specific distance scale in the early universe. Yeah? There was the particle horizon, which is given by the propagation speed of just the speed of light. This is the causality scale. The sound horizon is a little bit smaller, because sound in a relativistic fluid travels at a speed that's 1/√3 times the speed of light. So it travels almost at the speed of light, but not quite. And so that creates for you this sound horizon that's a little bit smaller than the physical horizon. And so in fact, at the time when the CMB gets released, this sound horizon is a size of 50,000 light years. Remember, the age of the universe was 380,000 or 370,000 years. So the particle horizon is roughly 370,000 light years. This one is a little bit smaller, this extra factor. So it's a spherical shell of 50,000 light years. Okay? So now actually this spherical shell you can see in the sky. Okay? So there's a very nice thing, I think mostly for pedagogical purposes, that the Planck collaboration did. So what they did is that imagine, we saw many of these hot and cold spots in the sky. Imagine you carve out all of the cold spots. So there's actually, in this picture here, we're taking of order 10,000 of these cold spots, and you stack them on top of each other. Yeah? So you move them all to the same location. So there's 10,000 of these cold spots. You put them all on the same location. Of course, these spots are not spherically symmetric. They have some random shapes. But if you take 10,000 of them, the average picture becomes spherically symmetric because, of course, the shapes are random. So if you put them all on top of each other, you get this picture here on the left. Okay? In temperature. And there's also, ignore the right-hand side. The right-hand side is for polarization. It has more detailed information about these fluctuations. So let's just focus on the left. This is the stacking of 10,000 cold spots, and it becomes spherically symmetric. And it has a characteristic scale here in black imprinted. some size of this, yeah, where things are have much larger fluctuations. That's the sound horizon imprinted in the map. Okay, there's this physical scale that we actually see in the map. Is that clear? Yeah. Okay, and then these repeating peaks that we have in the power spectrum are just the Fourier space analog of, if you take a spherical ring in real space and you Fourier transform it, you will get periodic perturbations, so periodic peaks in the Fourier spectrum. You can do this as an exercise in one dimension. Just take some, something at a fixed scale. It creates this kind of, as he was mentioning, it creates one fundamental frequency, that's the first peak, and then it creates higher harmonics, which are the other peaks. But they're all reflecting just the fact that in real space there's a ring that was being created by the photons propagating a finite distance in the age of the universe. Okay. So this is what, at first order, what this picture is telling us. The precise pattern, if you look more closely, of course, the first peak is higher than the other peaks. Odd and even peaks have kind of alternating size, if you look carefully. There's an average trend that's very nearly scale invariant. So there's fine details of this picture that depend on the precise composition of the universe. So I've told you before that kind of today, this is what the composition of the universe looks like. We can take this and trace it back in time to the time before the CMB was formed and use that to predict exactly how this map will look like. And I just want to show this to you now in pictures. Okay? We have 5 more minutes? Or? Okay. Oh, there's a question. Okay.
Excuse me. What does this mean, the angular separation? What does it actually physically mean in this context?
What does it physically mean? It means what the word says. Yeah. It's if you have 2 points in the sky, they're separated by an angle.
Oh, okay.
And so that's the angular separation. So for example, if I look at opposite points on the sky, they're separated by an angle of 180 degrees. This is actually something we don't see in the power spectrum because 180-degree fluctuations are just being created by the motion of the solar system through the rest frame produced by the. So there's actually larger fluctuations coming from our speed. We can measure our relative speed, which is kind of roughly a few hundred kilometers per second, relative to the CMB. That produces a huge Doppler, high temperature in this region when I'm moving towards the radiation, and low temperature in that region. Usually we factor this out because we just use this as a measurement of our absolute speed relative to that. And then the next fluctuation is 90 degrees. Okay, that's an L equals 2 multiple moment in spherical harmonic language, and then it gets smaller, smaller, smaller as we move to the right.
So it references the size of the cold spot?
Roughly speaking.
Okay.
It's actually a 2-point correlation. So, and the size of a spot is like more like a 1-point feature. So it's not quite that, but it's related. So the 2-point correlation, sometimes in simplified language, this x-axis is being described as kind of, sometimes in a popular talk, I might describe this picture as just saying that the y-axis is counting the number of spots of a given size. And then on the x-axis is the size of the spots. Okay. Just to not introduce the concept of a 2-point correlation function. It's roughly okay to say that, but it's not quite what this is showing. Okay, let me move on. Okay, so now I want to show you a couple of pictures of these stacked maps by varying the composition of the universe in my computer. Okay, so for example, imagine we do something very drastic and we take out all the dark matter. How would this picture change? Okay, so on the left, I'm always showing you what the data actually looks like. Okay, and actually here I'm showing you, I think, maybe the polarization map, so it has more features than what you saw on the left-hand side. So I'm showing you the right-hand side picture. But okay, on the left, there's the data. On the right is my simulation. Actually, not mine, the people down there that I cited. On the right is the simulation when I take all the dark matter out. Okay? And you can see by eye that these things don't match up at all. Okay? So that the universe we live in clearly has to have some amount of dark matter in order to explain these patterns. You can also see this at the level of the power spectrum. Yeah? So there's here now 2 curves. One is the curve that matches the data in red. It has about 32% of the total energy density in dark matter. There's a parameter that we use called omega m that measures the amount of dark matter. If I set this omega m parameter to 0, okay, I'm generating the blue curve. Okay? And that's not a good fit to your data points by any stretch of the imagination. Okay? And so you can see definitely we need some amount of dark matter in order to to explain these maps. Okay, and anyone proposing that there's no dark matter has to explain this, and often they don't. Okay. Now I can do the same trick with dark energy. What happens when I take all the dark energy out of my simulations and compare it to the data? Again, by eye, you see these stacked maps look very different, and also the measured power spectrum looks very different from the predicted power spectrum. And that's, very roughly speaking, how we determine the amount of dark energy in the universe, by fitting to the data and extracting the parameters from those fits. Of course, in reality, we fit everything simultaneously. So we have a 6-parameter model, and we fixed all the 6 parameters simultaneously to have a best fit to this curve. Okay, but this is just showing you visually that if I do something very drastic and just completely remove one of the components, it does not explain this data. And then, of course, that's also consistent with what we saw in the last lecture, that there's kind of supernova explosions that show that the universe is accelerating, and with exactly the same parameter that we infer from the CMB, we consistently predict or explain this curve of the supernova explosions. Okay, and again in red with dark energy, that's the correct fit. If I take all the dark energy away, I predict the blue curve that doesn't fit. Next parameter that we have is baryons. Imagine we take all, that's pretty drastic. We take all the baryons away, so that means us. Okay, but if you in a computer, of course, we can do this. So if you commit suicide and kind of take all the baryons away, then you also see that these things don't match up. And by trying them to match, you can measure the amount of baryons, and you can compare it to BBN, because BBN is an independent way of measuring the baryon density. And so there's a consistent measurement of the CMB baryon density and the BBN measurement. So those were 3 parameters. I've showed you kind of dark matter, dark energy, and baryons. There's 2 more parameters that describe the initial conditions. So this is something we will discuss in the lecture in a few hours, that in order to, of course, really predict this spectrum, there's some initial Fourier amplitudes that we have to input into our codes. Okay? But we can also use the measurements to infer what's the most likely initial power spectrum that explains this curve. Fortunately, kind of this initial power spectrum is exceedingly simple. Yeah. In particular, it has almost no dependence on scale. Yeah. So at 0th order, it's really scale invariant, that the power is the same on all scales. So if I had done the same as I did previously of stepping through different bands and showing you a picture, it would just be a picture that has the same intensity in all fluctuations, okay? Where there's no kind of change when I go through a peak and a trough, okay? So what we also discovered, though, that it's not exactly scale invariant, but at 1% level, it's slightly tilted. And so that's what I've indicated if you look closely here on the left. That is not exactly a horizontal line, but there's a little bit more power on large scales or small wave numbers, so on the left of the graph. So it's tilted like that. And then I've also indicated in A, B, C, D different wavelengths, and each wavelength is in the 1-to-1 correspondence with a feature on this map. So the largest wavelength fluctuations in the CMB occur kind of point A, and then there's B, C, and D that map the initial conditions to kind of this featureful spectrum. But the features are completely explained by kind of this plasma physics or fluid dynamics sound waves that I kind of was sketching. So that is the error that's called evolution. So, okay, so there's 2 more parameters that describe these initial conditions. There's an amplitude AS and then a scale dependence, or sometimes this is called a tilt of the spectrum NS. And so the amplitude is measured to be 10 to the minus 9. That's roughly speaking just measured by the density fluctuations in the early universe, or the CMB temperature fluctuations. And then the scale dependence is, has this value of 0.96, okay? It would be actually more natural to define NS to have a scale invariant value of 0. But as you can see here, for historical reasons, kind of this exponent here was defined with a -1. And so therefore the NS value is centered around 1. Scale invariance would be 1. The deviation from scale invariance is a deviation from the value of 1. And so here I'm just showing you different values of the different shapes of the spectrum when you change the spectral tilt around 1, and you can see how it tilts the entire spectrum, and so we can use this kind of tilt to fit to the data and extract these values. Okay, I just have one more slide and then I'm done. So this is just to summarize that the standard model of cosmology has 5 parameters, and I've kind of roughly sketched to you how those parameters are extracted from the CMB. So there's 5 interesting numbers that describe the amount of ordinary matter, the amount of dark matter, the amount of dark energy, the amplitude of the density fluctuations, and then also the scale dependence of the initial density fluctuations. And so what I think is worth emphasizing is that none of these numbers is well understood. So it's a very simple model in the sense it has only 5 parameters. The standard model has like 19, it's worse, okay? But in comparison, kind of all of these numbers are somewhat mysterious. So first of all, the amount of baryons is dictated by the matter-antimatter asymmetry. And as I mentioned last time, we don't know exactly the mechanism that produced this asymmetry. We don't, of course, know what dark energy really is as a particle, okay? We know even less about dark energy. So we can assign numbers to these densities, but we don't have a good microscopic descriptions for them. And then also we don't know what the origin of these fluctuations was, okay? So we will discuss in the next lecture kind of one proposal for what created those fluctuations that then predicts values for AS and NS, but it's more speculative than the rest of cosmology. So arguably none of these 5 numbers is well understood. Okay, so let me stop here.
Okay, we're really over time, but well, you already had your question. Okay, that's the one.
I just wanted to ask if, by using our observations of the cosmic microwave background and our observations of the galaxy clustering and so on, is there a way to estimate the absolute amount of matter out there?
Yes, totally. If you add up these first 3 numbers, you will notice that you get 1. Okay.
I think the dark matter includes the baryonic matter here.
Oh yeah, sorry, we don't add them up. Yes, exactly. So yeah, the dark matter includes this is the total, omega m here is actually the total matter density including dark matter. Thank you. Okay, if I add up the next 2 numbers, so omega m and omega lambda, I get 1. That's indicative of a spatially flat universe. And then I can use the Hubble constant, as we did at the very beginning of the last lecture, to get the average density, yeah, the measured Hubble constant. And so yeah, we have weighed the universe. We know exactly how much matter. Then we know the average density. It's then 5 protons per cubic centimeter, and you know what a proton weighs. And so we know. Yeah.
All right, let's go for coffee, and we'll be back shortly.